I'm Chanakya. My project is DCP DRS. It means Dark Channel Prior Dehazinger Restoration System. So we are tackling one of the most persistent problems in image processing, that is atmospheric degradation. So our goal was to design an engineered solution based on physical principles and not just based on filtering. Okay, so the entire system is rooted in the atmospheric scattering model, so which mathematically describes how distorts a clear image. So as seen here in this form, I can see here. So I of x is equal to g of x into t of x plus a of 1 minus t of x. So I of x is the observed hazy image. So g of x is the desired haze free image. So which is the system's target output. So t of x is the transition map, which is like a light fraction reaching the camera related to the scene depth, and A is atmospheric light, the ambient color or intensity of the haze. Okay, so we must solve for the clear image g of x by estimating the two unknowns. The two unknowns are the depth t of x and the haze color A. Okay, so we achieve this by using a dark channel prior DCP. So our first step is to calculate the DCP map itself. So you can see the DCP map here. DCP map here, right? So this map is crucial because it confirms the underlying mathematical assumption, like the bright areas correspond directly to the densest haze and the dark areas are our reference points. So for clear objects, this is what actually assumption, right? So it confirms the underlying mathematical assumption, right? So that's why DCP is very important here. So next what we'll be doing is we'll be deriving the raw transition map. So this map is essentially our estimate of the scene's depth. So however, this initial map is blocky and mathematically imperfect, so which would lead to severe halo artifacts in the final image. So to resolve this, so we implemented a refined layer, the another next layer. So we use the guided image filter to smooth the transition map. So this is a critical technical achievement, I would say, because the filter elements blockiness and noise while precisely preserving the sharp edges of the objects. So which ensures an high quality depth map. Okay, fine. So you can see the dark channel map here, raw transition map here, and as well as the refined transition thing. So you can see the output here, restored image, g of x. So the original has image and the restored image you can be able to see here. Just so okay, fine. So now let's move on to the final product which we have built, which I built, the Streamlit web application, right? Fine. So this is the interface of the Streamlit web application. So now let's demonstrate the final product. So the user interface is like designed for like real world application and control. So I'll be hosting this and posting the link in the description as well. You're free to use it. Okay. So the first thing is I'll upload a hazy input image here. Okay. I'll use this particular anything is fine. So this thing we have used in the document, right? So let me use anything. Okay, fine. Or else I'll be using the same thing. I choose the image, fine. So the processing is governed by two primary parameters exposed here, like you can see the omega, so which allows the user to tune the dehazing strength in real time. So rather than the hard-coded ones based on the different images, they need adjustment, right? So this controls the severity of the correction applied by DCP formula. Okay, so we also expose the guided filter parameters here. You can see here. So which is the filter that fixed our halo problem, right? So I'm also going to show intermediate maps. So which is on. Okay, so I'll click on process image, right? So this is the original has image, and you can see the restored image, how clear it is, right? So from when combines to original image, so the system executes a like complete pipeline which I had explained previously and delivers the restored image. So this is the restored image. So you can immediately see the dramatic increase in contrast and removal of the atmospheric veil. This high fidelity result is achieved through precise and artifact free transmission map we generated, right? So we also designed the application for transparency. You can see the intermediate maps here, so you can click. There's nothing like close thing. So what actually the process through what the pipeline output is at every checkpoint, you'll be able to see that actual DCP output, raw transition map, and then the refined transmission map as well. Okay, fine. So we confirm the dark channel correctly identifies the hash, you can see here, right? So and we confirm that the refined transmission map is perfectly smooth, so which validates that our guided filter successfully integrated the physics with advanced spatial filtering, right? The DCP-DRS is like modular high quality system ready for application which can be used to dehaze your images, right? So I'll just show another choose another image as well. Okay, let me choose this, fine. Right, fine. See the result here. So you can see haziness in the original image, you can see the clarity in the second image. Yeah, there are a few parameters which needs more fine tuning, which differs from image to image, but the core and final restored image is mostly dehazed one, right? So let me choose another example as well. So you can see this image is of like very less resolution, but yeah, you can see the dehazing image. You can see the clarity, right? Thank you. Thank you. I will provide the link for the document, and after hosting this application, I will paste the link. I will just upload the link in the description, or else I'll give in the pinned comment. Yeah, thank you for watching.